unmuted.
You can be. You needn't be muted. It's fine.
Yeah. I'm okay now.
Yeah, perfect.
Okay.
We are just going into on YouTube.
Yeah.
You needn't be muted. It's fine. Welcome back to the last session of our code day. We are privileged to have Professor Balasubramaniam Ananthnarayan from Indian Institute of Sciences with us today. He has been the chairman of Center for Theoretical Studies at the Indian Institute of Sciences, Bengaluru. After obtaining his MTech from IIT Madras in chemical engineering, Professor Ananthnarayan did his master's in sciences and physics from Delaware University, USA. And then he got his PhD from the same place, Delaware University, USA, in physics. He returned to India and did a postdoctoral fellowship at PRL Ahmedabad and then joined IISc. Professor Ananthnarayan is an associate member of International Center for Theoretical Physics, Trieste, Italy. He has been visitor at the Thomas Jefferson National Accelerator Facility, USA. He's been the recipient of the fellowship of the Homi Bhabha Fellowship Council. Today he'll be talking to us on joy of discovery in modern research. We are privileged to have you with us, sir. Thank you.
May I start now?
Yes.
Yeah, and the audio and video are they are clear. The screen is okay.
All is fine. Perfect.
Okay. So thank you very much. It's a great pleasure and honor for me to be speaking at this refresher course, and I would like to thank my friend Professor Najam Hassan for thinking of me for this event. I'd like to begin by saying that I come from Hyderabad, so it is also a great honor for me whenever I have an invitation from there, and it's a privilege to be speaking at an event hosted by the Maulana Azad National Urdu University. Since this is a talk for people who are already engaged in science as well as in teaching, and it's a refresher course, although the slides are those that I have used use some of the material in the slides as pedagogical tools, and what is the approach that teachers should take in order to convey the excitement in research. And as it is a refresher course, I will point out the things that they probably know already in their training. They may have had bits and pieces of it, but what it is that they must think about. Actually, it is also kind of a coincidence that we are having this this refresher course in the heart of the Nobel Prize season, and it's particularly interesting that the Nobel Prize in physics was awarded day before yesterday to Roger Penrose, who's one of the great doyens of the subject. He's 89 years of age, and also for two younger researchers, Reinhard Genzel and Andrea Ghez, for their discovery of supermassive black holes at the center of the Milky Way galaxy. In fact, some of the examples that I use actually do depend on these kind of celestial objects. So it is also topical and nice for us to think about this. So Roger Penrose, in his work, he had actually studied the Einstein equations, and he had shown by studying the mathematics behind these that these objects known as black holes will form in the universe in various circumstances. Now, black holes, just like many other celestial objects, come in a wide range of sizes, and typically one speaks about the size of the black hole mainly in terms of its mass. Actually, all you need to describe black holes, which are very pristine objects, are their mass and the angular momentum that they carry. So the mass of these objects that are at the centers of galaxies is the orders of millions of solar masses. Now, this may sound like a big number to you and me. It's actually not such a big number, because the mass of the galaxy is several orders of magnitude larger. In other words, the presence of supermassive black holes, even though it conjures the idea that these are really, really enormous objects or very heavy objects, actually contributes almost nothing to the mass of the galaxy itself. But from the point of view of the existence of black holes and the point of view of detection of these are revolutionary, that we had to wait till the 21st century for us to establish the fact that black holes, which theoretically are known to form, that they have actually been detected. Not only have they been detected, but the examples that I will talk about also talk about not just the existence of black holes, but also their participation in very violent phenomena in the universe, such as the merger of black holes. And that is what I'd like to talk about. I understand that in this particular refresher course, we have members coming from various branches of science, from biology, as well as from mathematics and physics and chemistry. But what we would like to have in this talk, although many of my examples will probably come from mathematics and physics, I will also have examples from other disciplines, is we want to think about the method, you see, of how do we approach science and how do we teach science in this particular discussion. So that is the emphasis of my talk, is how do we think about it? Never mind if you don't know the details of a particular topic that I'm talking about. What we need here is to think about the approach and how do we approach this whole issue of science as human beings, as sentient beings, where our minds look and think about the universe, think about phenomena, puts them together. So it's our minds and our brains which are actually supreme in this particular game. Yesterday, you must have seen the Chemistry Nobel Prize, which was given for work done in biology. So there is something to be learned there also, that you see so much of overlap between subjects that there is no clear distinctions between what is mathematics, what is physics, what is biology, what is chemistry. So there's a kind of a unification of subjects also, and interdisciplinarity. So let me begin by quoting for you from a very famous 19th and 20th century mathematician, primarily in the 20th century, because he lived in till about 1940 or 45 or so. So he had these very memorable words. So he says, we must know, we will know. So here you see in these simple words, he has captured the essence of what it is to be human. That is, we have the urge to know, and we also have the will, and we have the methods and the determination to know. So this is a quote from David Hilber that I wanted to talk about. I'm also showing you a picture over here of a person that we all ought to know, but we really don't know who she is. But later on in this talk, I will point out and tell you who she is. I'll give you a hint that she basically determined the stuff that much of the universe is made of. She's that important. So with her work, she kind of figured out the stuff that the universe is made of, and yet she remains kind of unknown in the public mind. So in this, as teachers, we all have to figure out what are all the various things that we need to talk about? What is it that we have to do in order to inspire younger people? And how do we convey the excitement of doing science? As teachers, it is our responsibility and our duty to do that. So I wanted to start out with this example, already about more than 4 years old. And this had to do with another example from the general theory of relativity, which had been predicted by the Einstein theory, not by Einstein himself, but by others. Ladies and gentlemen, he said, we have detected gravitational waves. Actually, the calculation was probably done by Einstein, but he didn't think that we would ever have technology to actually discover what are called gravitational waves. So he says, we did it. These are the words with which he conveyed his excitement at one of the greatest discoveries in science in the 21st century. This was David Reitzer when he was speaking and reporting on the discovery of gravitational waves, which happened in his laboratory in the apparatus on September 14th of 2015. I also want to emphasize that the actual event was seen by a very young person. He was a young researcher in this experiment called LIGO, which stands for the Laser Interferometry Gravitational Wave Observatory, LIGO. Now, actually, India is also a partner, and we will be building an India station for this LIGO experiment, and will participate in this international collaboration. And he confirmed a prediction of the general theory of relativity made about 100 years ago. Now, we all know what the general theory of relativity is in a sort of it's now part of culture about how light bends when it goes around a very massive object, or the precession of the perihelion of Mercury. And also there have to be corrections to GPS, which is there on your smartphones because of the general theory of relativity, the fact that satellites are in accelerating orbits when they go around the Earth, that there are these effects due to the bending of space-time itself. So now it's a part of general culture, what the general theory of relativity is supposed to convey. So what was seen at that time was gravitational waves due to the merger of a binary black hole system. And I want you to keep an eye on these numbers. So as teachers, you also have to have familiarity with numbers because you have to convey this to your students also. So there, it was a binary black hole system, which means that there are two objects participating because it's binary. So as I said, black holes are primarily described by their masses. So there are two masses here, one of 36 and the other of 29 solar masses. Now, if you add 36 and 29, you're supposed to get 65. But in this merger, what happened was that there was a new black hole, not of 65, but 62 solar masses. So you may be wondering what happened to this difference, the deficit between the 65 and the 62, the three solar masses. Well, what happened is that it disappeared into gravitational energy, that in this cataclysmic event of the merger of these two black holes, 3 solar masses worth of mass just disappeared into gravitational energy. This was very far away. So imagine that the energy that came from there actually shook all of space-time itself. So that is what is meant by gravitational waves. And that is what we are trying to detect on the Earth, on terrestrial man-made equipment. So you see, so you look at what is going on over here. Very far away in the universe, there are two black holes. They merge. And in that merger, the energy that is released, it's like a blast that reverberates and echoes into the far reaches of the universe, has to be seen. So whenever there is a blast, what happens? Things shake, right? So basically, the principle of this LIGO experiment is to look at the shaking of space-time itself. And it was because of improvements in technology and laser interferometry that it became possible to find this shaking of space-time itself. And soon afterwards, there was a Nobel Prize already 2 years ago, maybe it was 3. It was awarded to Kip Thorne, who was the experimentalist, who was a theorist that constantly talked to experimentalists to get this experiment done. These two people, Rainer Weiss and Barry Barish, they won the Nobel Prize for this discovery. So I'll also show you pictorially what this thing looks like, just to keep things going. So here are pictures of the founders of general relativity and black holes. So believe it or not, even Albert Einstein, who's shown on the left over here, was once a young man. So this was actually around the time when he set up the special theory of relativity. 10 years later, he had established the general theory of relativity. There was a time when he even had black hair and he wore a checked suit, I guess. And then the black hole was first sort of postulated and found by this person, Carl Schwarzschild. Now, this is the year 1916 when Schwarzschild writes down his solution. Einstein's theory is in 1915. And as you might imagine, this was all in the middle of the First World War. The First World War was from 1914 to 1918. So this was in the middle of the First World War. Schwarzschild does his solution within a year of the discovery of the general theory of relativity. He finds a static solution to the Einstein field equations. And that today we know is a black hole. And the radius of such a solution that we call the black hole is called the Schwarzschild radius in honor of Carl Schwarzschild. But the poor guy, soon after that, he got a disease when he was out in the front during the war and passed away very soon afterwards. As I said, this was a static solution that was given by Schwarzschild. And then the rotating solution was found much later in the 50s or 60s by Roy Patrick Kerr. who fortunately is still alive. He was from New Zealand. He found the other solution, which is of interest, which can exist in the universe, which is called the Kerr solution, which is that of spinning black holes. So this is a pictorial depiction of a black hole merger, that these two black holes get together and then they fall into each other and coalesce. And in this gigantic merger, the entire space-time begins to vibrate, and you can see the ripples spreading outwards from this merger. And it's when this ripple hits the laboratory equipment of LIGO that we see the solution. So this LIGO consists of two observatories separated by many thousands of kilometers. One is in a place called Livingston in Louisiana in the US, another this is in the southeast part of the US. This is in the northwest part of the US, in a place called Hanford. And you can see here the shaking of space-time. So the important thing for physics teachers to ask themselves is, what is the principle behind this laboratory experiment and interferometry? So this uses very accurate lasers which lock in on each other. And they are so accurate is that if nothing shakes, there is no disturbance. If everything else is subtracted out, there'll be a completely flat signal. And what happens is when space-time itself is shaken, you see what the shaking looks like. And you can see that these two stations, even though they are separated by 3,000 kilometers, see the same signal. And they are separated by a millisecond or so, which means that this explosion, the ripples come and hit your laboratory first in Louisiana and then in Washington, that there has to be a delay because there's a finite amount of time taken for the signal to go from one place to the other. So these are the principles of this experiment which science teachers should think about. The various aspects of this, I hope that some of you will write down these notes and then go and read these for yourselves. The principles are straightforward. You can actually teach yourself what is really the scientific principle behind the LIGO experiment. So here you can see the map of the US on the Earth, and here is Louisiana, and here is the Washington stations. And these are the pictures of the Nobel laureates at the time of the prize. And then it seems that you have to be old and you have to be white and you have to be bald in order to get the Nobel Prize. But yes, today the chemistry laureates prove that these need not be true. Certainly you can be a woman and you don't have to be gray and you can have hair and still get the Nobel Prize. Now, these are not the only objects in the universe where this kind of merger can take place. What we talked about until so far was about black holes. There are other objects in the universe, such as neutron stars. And neutron stars can also produce, they're also very massive objects. They can also merge, but the difference between the black hole merger and the neutron star merger is that black holes are objects from which nothing can escape. So the only information you will get about black holes is from objects that are outside the event horizon of the black hole, and nothing can escape it. So there's no light or no other kind of probe that will tell you that a black hole was there. On the other hand, neutron stars are exotic objects in the cosmos, but they can produce other signals also in their merger. So you can simultaneously look at the gravitational signal coming from neutron star merger and also signals coming from, say, the electromagnetic spectrum. And we have the birth of a new subject now, which is called multi-messenger astronomy. This is very interesting for those of you who are teachers in the audience. You should follow some of these developments about what is meant by multi-messenger astronomy. There are many websites dedicated to these things. You can see, the range of probes that are used. For instance, in the electromagnetic spectrum, they have a space telescope, then they have the gravitational telescope, of course. Then they probe information coming from neutron star merger in the infrared, in the radio, in the X-ray, and so many other regions of the electromagnetic spectrum. So one of the people who had proposed studying neutron star merger was awarded a very important prize, which was called Eddington Medal, for proposing this kind of a study. So for those of you who are at the refresher course who are looking at the most recent developments in physics and astronomy, certainly study this topic known as multi-messenger astronomy and see what goes on. on over here. In order to really get a hang of human life, of the universe, and so on, we ought to just step back a little bit and see what is the story that we are interested in, what is it that we are talking about in this whole game, what is meant by physics, what is meant by astronomy, what is meant by cosmology, so on. So you can ask yourself where it all began. So it all began in something called the black hole, which is the Big Bang, which is again associated with the work of Roger Penrose. This time Penrose work done along with Stephen Hawking, where they applied the equations of relativity to the universe itself, the cosmological solution, and they proved that the Einstein equations do admit solutions which can lead to a big bang. That is, if you run the clock backwards, you do end up in a situation where the entire universe could have been born from a big bang. So that is what is over here at the bottom of my slide. And after evolve, and you can see over here that here are the various epochs of the universe. As a Planck era, what is called the grand unified era, then the various forces that elementary particles experience among themselves, how they separate out. There are these electroweak era, and so on. So you can see that this is the story that we are talking about over here. And here on the right side, you have the various important epochs in the universe. For instance, here where the first galaxies began to form 1 billion years after the birth of the universe from the Big Bang. Now, a useful way of trying to remember how old the universe is, I always remember it as 10 to the power of 19 seconds. That's the age of the universe. So you can see that this is relatively recent that the galaxies began to form. There's a long time that elapsed between the Big Bang and all the forces and gravitational interactions and so on separated out before galaxies could have formed. So what are the various scales in the universe? So you could ask yourself the question, something that you may need to convey to your students also, from the smallest to the biggest. How do since here is a very useful way of looking at things. Quarks are very small objects. They are constituents of, say, protons and neutrons, which in turn form nucleons, which in turn form nuclei, and nuclei in turn form atoms. And from atoms, you get crystals and matter. So that is how you can get a sand grain over here. So here is a sand grain starting with a quark to the next objects in this hierarchy of structure, where you can get a nucleus, and then you can get molecules and grains. And you can see sand grains. Here is a beach. Sand grain sitting over here. So here you can see what this length is. It's 5 times 10 to the minus 4 meters, whereas there's roughly a meter. You can see a human footprint, and you can see the sand sitting on the earth over here on the beach. And here is the earth sitting in the solar system like that, Jupiter, the biggest planet. So we are over there orbiting the sun, going round and round. And here is the solar system, which sits in one of the outer arms of this spiral galaxy that we call the Milky Way. And the Milky Way, of course, sits in something called a local cluster of galaxies, which sits in a supercluster of galaxies. And these superclusters sit in the universe itself, like so. Okay? Right. I think so. One of the participants seems to be having the camera on. I request him to turn it off. It's a little distracting. Okay. Now let me turn to another important scientific discovery that took place some years ago. So here I was talking about the universe at the larger scales. But in order to understand the universe at the larger scales, you want to know the laws that operate in the microscopic world also. Of course, we have, solid state physics. We also know nuclear physics. But we really want to know what are the basic laws that allow elementary particles to interact with one another. So in this regard, we have built something known as a standard model. The electromagnetic interactions and the weak interactions, which are responsible for subnuclear decay, are all unified in something called the electroweak interactions. This was work done by Abdus Salam and Sheldon Glashow and Steven Weinberg. But they had made a prediction in order to make the theory work, which was to make the force carrier of these forces to be massive. And it had to have a sector that predicted the existence of a particle known as the Higgs particle. So for a long time, we had not seen this directly because there was no experiment which had sufficiently controlled beams of sufficiently high energy in order to directly produce this particle. So this experiment, which is called the Large Hadron Collider at CERN, CERN is the European Center for Nuclear Research. This is the acronym in French. Actually made this discovery in the year 2012, even though the existence of this particle was made in 1964. It took nearly 50 years of very concentrated effort in order for us to build an experiment where we could actually find such a particle. So again, I want to emphasize over here that in order to really understand the laws of nature, it requires a very dedicated and a long-term investment and commitment and a lot of patience in order to kind of validate theories that have been set up in order to describe nature. So that is what I try to say over here. Is everything going all right? May I ask Dr. Najam Hassan, everything all right? Okay, fine.
All is fine. We can hear you well and we can see everything.
Okay, thank you.
Thanks.
So I just wanted to emphasize here, especially to the teachers, that you must think about these things. You know, just look at a newspaper article and just accept everything over there. You must read these things critically and use your mind to ask yourself, oh dear, it really took 50 years for this to happen. If so, why? Why does it take so long for us to figure out these things? So teachers must also familiarize themselves with the important and leading discoveries of the era so that they are really on top of things, and then they could then convey this information to the students and make science a living, breathing entity, not something sitting in very boring old textbooks. So that's the reason why I've decided to talk about these also. And also it's important to recognize and emphasize and to convey the fact that in order to carry out scientific discoveries today, we need a lot of technology. We need cooperation of many countries or many scientists. For instance, this acronym that I have here on this slide, CERN, is the European Center for Nuclear Research. It is not any one country, you see, it's an entire consortium of countries who have all come together and pooled their resources. So we are in an era of a lot of collaboration, cooperation, not just between individuals, but also between laboratories, between countries. So you see, the enterprise of science is very different from what it used to be, let us say 100 years ago. That is why we talk so much about Einstein and Schwarzschild and so on, which is of course fantastic, but today science is done in a different way. So this also led to another Nobel Prize to two persons, to Peter Higgs and Francois Englert. The work of Englert had been done in collaboration with Robert Brout, but sadly Brout had passed away before this discovery took place. And the paper that appeared is given in the order of Englert and Brout. Now you may say that, gosh, this is strange, because alphabetically it should have been Brout and Englert. But no, even though Robert Brout was the thesis advisor and Francois Englert was his student, this man was so great that he told the student, you go first. You know, so that's a paper of Englert and Brout. So here I also want to emphasize the human aspect of scientific work, scientific research, that there's a degree of selflessness that is needed. There's also, in the previous instance, I talked about the First World War. Now, some of these events are against the backdrop of the Second World War. Englert was from Belgium, and during the war, he had to be in hiding because his life was in danger. And he came from such a background and made such a path-breaking discovery. So this is to say that there will always be challenges. The human condition is like that. There will always be challenges. Every generation will face a different set of challenges. And we ourselves are facing this COVID challenge where life has been completely thrown out of gear. But we have to take into perspective a long-term view that 10 years from now, you will look back and say, oh, okay, there was this COVID period, but I didn't allow it to beat me. I used it to do many useful things. I mean, COVID is nothing compared to the Second World War, but still, what I'm trying to say is that history will not forgive us if we don't overcome the circumstances that we find ourselves in. So he's in the middle with the blue tie, and this is Peter Higgs, who's not wearing a tie. And on the left is Rolf Dieter Heuer, who was the then Director General of CERN, just as the conference was beginning. The discovery of the Higgs particle was going to be announced. Now, what is this Hadron Collider? Large Hadron. Here, protons are accelerated and then they are collided. So it's a Large Hadron Collider. And here is a picture. Here are some mountains in Switzerland, I suppose. Here is the Lake of Geneva. And here is the experiment. This has a circumference of 26 kilometers of these two rings in which the protons are accelerated. So once again, I want to draw your attention to the complexity of these experiments. I mean, once I break it down to this, perhaps, you can see how difficult these things must have been from an engineering point of view. They're deep down in the earth, deep under the surface of the earth, and it runs under two countries. Here you can see the flag. There is Switzerland, and then there is France, and this ring runs under both of them. There are two important experiments. One is called the ATLAS, which is a toroidal LHC apparatus. That is what ATLAS stands for. And the other one is called the CMS, or the Compact Muon Solenoid. Now, all of you, everybody who's had a high school education, knows that there are two kinds of magnetic fields. One is a toroidal field, other is a solenoidal field. So you can see that these two experiments have complementary principles, one based on a toroidal magnetic field, another on a solenoidal magnetic field. And there are several other experiments also, which I'll not talk about. So these are pretty big experiments. And these are the facts of the LHC, which I've already said in words. So I probably don't have to repeat them again. But anyway, the LHC, some of the facts that I can repeat for you. It's an accelerator running under two countries, Switzerland and France, with a circumference of about 27 kilometers. You can imagine the engineering feat of building a scientific experiment whose circumference is 27 kilometers. But that's possible today because of the improvements in all kinds of things, right from the technology for digging and the technology that involves magnets, magnetic fields, the precision and the clean environments that are needed. And you can see that these are some of the world's most technologically advanced countries. So it is also normal and natural that some of these experiments are done in those countries. The USA, of course, is the world's most advanced country technologically. And they did a lot of work for several decades, but now they're doing work more concerned with observations, space probes, and also
We can't hear you. None band ho gaya. Just stay tuned in. I think there's a problem at the speaker's end. Probably he lost his connection. He should be back soon. I think there is some net issue at the speaker's end. So just just be online. Yeah, he's back. Yeah, we lost you for a minute. You'll have to unmute.
Yes.
And
Hello. Yes. Yeah.
yeah,
Do I have to share screen again? Yeah.
Yes, I'll.
Yeah. Is that okay? Am I sharing the screen again?
Yes.
Okay. So sorry about that. So it started complaining about unstable internet, and then it threw me out. So anyway,
So
thank goodness for this
if
internet
there is a
connection.
problem, then you
Yeah.
can switch off your video. If your
Yeah.
net is giving issues,
Oh,
then
okay.
switch on the camera after the presentation.
Okay. But for the moment, I've switched to the hotspot. I hope that's
Yeah.
sufficient.
No, we'd love to see you there speaking, but in case you need
Yeah.
bandwidth. Okay.
Okay. Okay, so let me continue now. I hope that it doesn't throw me out of this, but anyway, let me continue for now. So anyway, so these are the goals of the Large Hadron Collider, was to test the standard model at the high precision and to look at the mysteries of elementary particle physics, search for extensions of the standard model. And I think it has done a very admirable job of many of these things. So these are the many or the 7 experiments that I just noted down over here, for especially for science teachers who may be interested in conveying the important features of what is probably the most important particle physics experiment of the era. So you can read about each one of these. CERN, Fermilab, they all have really wonderful websites and a lot of educational material. And I'm sure that you would be able to look over there. It's highly accessible. In fact, part of the mandate of these national laboratories and international laboratories is outreach, and there's always material available for those who are interested in learning and conveying this material to others. So I'd like to encourage the participants of this workshop also at the Refresher School also to look at these things and to learn these subjects and to look at the principles that each of these experiments uses and what science they are going to undertake. I also want to capture for you with pictures what is the scale of the scientific enterprise. So here is, I could have picked any one of those detectors, but I just picked CMS just at random, partly because India is a member of this CMS collaboration, the Compact Muon Solenoid experiment. So I just thought that perhaps we should also highlight our contribution. So this is what the Compact Muon Solenoid looks like. Any particle physics detector is basically a large camera. What it does is it detects the particles that are produced in the collision of other particles. And because of Einstein's theory of relativity, you can take particles of a particular species, convert the mass into energy, and then that energy is converted back into particles, familiar particles, and you detect them. It's as simple as that. So that's the principle of detection. So here you can see the various particles that it would detect. For instance, it would detect muons, which are heavy cousins of the electron, large number of muon trackers over here. So here is where 2 protons would come and they would collide over here. And in this collision, large numbers of particles would be produced. And then this camera would capture the picture of these particles that are produced. So what's the size of this camera? Well, you see here is an average human being standing close to the compact muon solenoid. So you can see this camera is very big, much, much bigger than an average human being. So the overall length that is shown over here, as you can see, is about 21 meters. That's the length of the detector over here. A human being on an average is less than 2 meters. So that's who you have over here, 175 centimeters, 160 centimeters average human height. So here is the overall diameter. All these data is given to you. And it's a very strong magnetic field. It's present inside the detector because when particles are produced, they are charged. And these charged particles will have to curl out in magnetic fields. That's the reason why the magnetic field is a very important constituent of these detection principles. These are what are called superconducting magnets, and some of them have been manufactured here by Kirloskar in Bangalore. So you see, Indian technology is also advanced, and it won international tenders to produce some of the components that go into the LHC detectors. In order to produce the Higgs, you also have to detect it. So this is the idea. It's a very simple idea that two protons collide against each other. The proton is a composite object. It has things called gluons inside them. And then these gluons collide with each other through this virtual presence of these particles, which are called top quarks. And then this Higgs particle is produced, which subsequently decays, producing two photons. So that's the idea, that to produce and see the Higgs, what you have to do is that you have to take mass present in protons, convert it into energy. Part of the energy produces these Higgs particles, and then it decays into objects, which are the photons, which the camera captures in its eye. So that's the principle that is explained over here, which every teacher has to try to absorb. Exactly what is the principle behind these LHC experiments? How do I learn it, and how do I convey it to children? So on that particular day, when the press conference, the data that was shown was this, that there were all these two photons that one was looking for, and as a function of the energy, you looked at the energy of the photons that you have detected. And if there had been no Higgs, then it would have been this dashed red line in the number of events that you have seen of the number of photon pairs that are produced, that are correlated photons are produced. So if there had been no Higgs, then you'd have seen this dashed red line over here. But actually you see a bump over here, and then you can subtract the theoretical curve over here in the absence of the Higgs, and you actually see a big bump like this, corresponding to your having produced a Higgs particle of mass of 125 GeV. And this was the prediction of the Higgs theory. Higgs had predicted everything except the mass. It was a free parameter of the theory. He had no way of telling in advance what the mass of the Higgs could be. So it had to be experimentally discovered. And that is what was done over here. There's an experimental discovery of the Higgs. So you see, I'm trying to convey the challenges of theory, of what theorists talk about, how an experiment has to be designed in order for a discovery to take place. So now I want to switch from these two experiments of LIGO and LHC and talk a little bit about science itself. What is it that we do, and how do we convey the excitement of doing science? So everything that I talked about, for instance, the CMS collaboration has about 4,000 scientists working on it, including students and postdocs and technicians and so on. That's a large number because it needs so many people to participate in understanding the data, subtracting out backgrounds, and finally saying that, look, there's a Higgs over here. Or the LIGO experiment, which has about 1,000 people on the author list. So this would convey the idea that anything that you want to do, you can only be part of a massive team, which is also true whether if you're working in Dell or if you're working in HP. It's all teamwork. And is it so that you need very complicated technology to do anything at all in this day and age? Well, of course, technology is there, but there's also a role. A person who participates and uses his or her mind in a very incisive way will have a role in a team also. But it's still possible to do have this 5 years, 30 years ago, there was high temperature superconductors, ITC as it is called, which is for thing called graphene, which are tabletop experiments. But even these have been made possible by advances in technology, single-mindedness, and perseverance. I'm not talking about science in the sense of what else we could do in the terms of observation of nature. In biology, in botany and zoology and so on, you don't need all these things, but that's a different way of doing science. Here we are talking about science as done in a laboratory under very specific controlled circumstances. So you can ask yourself the question, what is the role of the individual? What do I do? Where do I come in this game? Do I have any role at all? So the best way is to again take some examples and see what people who participate in these activities say about the nature of their calling and what is the key message of all this. This is also important for those of you who are interested in education. I can also say this because my mother, my late mother, passed away earlier this year. She was a teacher in Hyderabad. She taught at the NSR College of Education of the Vivek Vardhani Society. So she was very enthusiastic about her role as a teacher of teachers. So words like methodology and education and philosophy of science, this is something that I have grown up with. She even wrote a book on the educational philosophy, which was translated into Telugu and published by Telugu Academy. I don't know if it is still in print. So that's one of the reasons why I was very happy to have this opportunity to be able to participate in this refreshers course for teachers. So you have to, those of you who are registered participants, I urge you to think about all these. I'm not saying I have the answers, far from it. But what I'm doing is I'm at least asking you questions to see what role you could play. How do you motivate other teachers and other younger generation to get into science? Actually, one of the easiest things to talk about, because all of us have basic education in mathematics, is to take examples from mathematics, because it's also very, very romantic. And everybody understands basic mathematics. So let me take some examples from mathematics, which some of you may know, you may have read about. So we all know what the Pythagoras theorem is. For instance, 3, 4, and 5 are an example of a Pythagorean triple. 3 squared plus 4 squared is 5 squared. There are many others. 5 squared plus 12 squared is 13 squared, and so on. So it seems natural that if you have whole numbers and you take their squares and add them, that in principle it is possible to find one more whole number or an integer, which is also a perfect square. And this is as old as antiquity itself. It came down from Greek mathematics. It was known in Indian mathematics. It was known everywhere because it is also the principle for measuring land. And of course, land is the most important piece of property that anybody can have. So you see, mathematics is, in this case of the Pythagorean theorem, is so common. So the first question you can ask yourself is, are there other examples? Can you have whole numbers so that if you cube them rather than square them, or if you take the 4th power or the 8th power or the 97th power, can you find x, y, and z such that x cubed plus y cubed is z cubed? And about 400 years ago, this person over here, Pierre Fermat, claimed that he proved that it was not possible, that except for the case of squares n equals 2, which goes back to Pythagoras, you can never find a set of whole numbers so that the nth power of 2 of them will be the nth power of a third one. Now this, he was a judge, Pierre Fermat. So he, of course, most of his day was busy, probably listening to cases. But in his free time, he would do mathematics. And he did many, many important results in mathematics, especially number theory. But here he made this claim of this amazing thing. And he claimed he had a proof. He probably had a proof for 3 and probably for 4. But he made an audacious claim that this is true for all powers, all infinite number of powers. So that's where the catch is. I mean, you may be able to prove it for 3 and 4 that it's not possible. And in fact, a lot of work in the 19th century was done for very special cases. But it was not settled, except into the 20th century, into the late part of the 20th century. And the proof came from this person, Andrew Wiles. The picture is given over here, who had read about it as a child in a book in a lending library, that there was such a problem in England. And he said that, oh, when I grow up, I'm going to prove this. And it came from a long chain of ideas associated with 2 Japanese mathematicians, once again, post-World War. So imagine, there's a world war which has devastated your country. It has leveled 2 cities, Hiroshima and Nagasaki. And still, from those ashes, these people came up and talked about mathematics. They came up with a conjecture that's named after themselves. It's called the Taniyama-Shimura conjecture. And then they said they gave this conjecture, but later it was connected to Fermat's last theorem by a whole series of authors. And finally, it was Wiles who actually proved a special case of the Taniyama-Shimura conjecture, which was sufficient to prove the validity of the Fermat's last theorem. So you can imagine the kind of span of history that a result like this has. And he talks about his eureka moment in this BBC interview. There's another example from mathematics that I want to take up, which is actually comes from this century. So it is named after the French mathematician Henri Poincaré. So it has to do with the properties of surfaces in 3 dimensions and whether a 3-dimensional surface, 2-dimensional surface, of course, you can imagine. 3-dimensional is harder to imagine. 2-dimensional surface, whether it has holes in it or not, and in n dimensions. So this had been settled in all dimensions except in 3 dimensions. So there were some partial results, and this Russian mathematician Grigory Perelman, the early part of this century, he used ideas coming from physics, what we call renormalization theory. That's where it took birth, and he used those ideas. It is also related to Einstein theory of relativity and the kind of mathematics that goes into it. It's the coming together of 2 different streams of mathematics. So he actually settled this problem. And then there was a organization, a private organization called the Clay Mathematical Foundation, which had offered a $1 million prize for settling this problem. It has a list of 7 problems, of which only this one so far has been settled. There are 6 more for young people to find and settle. I urge you all to go and read about it at the Clay Mathematics Foundation. They have a very good website. You can go and read about it. So Perelman, although he settled this problem, he refused to accept his $1 million prize, and he also refused the highest honor for mathematics, which is called Fields Medal. Mathematicians, of course, we all know, are pretty unusual people. So here is one more example which added to the romance of mathematics. So you see, I'm trying to illustrate to you many different things: mathematics, physics, technology, science, and how we need to participate as individuals. We need to improve our own consciousness and rise and learn more and more about these things and try to put them together. Of course, we need to convey this to younger people. I want to describe now a handful of examples which are actually coming from a branch of theoretical computer science. Now, it's not very clear exactly what is theoretical computer science, what is mathematics, where does one end and where does the other start. But these are, again, examples that I can explain to you because anybody who has a high school education can understand this. This is not my field, but even I was able to read these and try to figure out what exactly goes on over here. The important thing in what I will discuss now is the need for interdisciplinarity also, to be able to borrow from different branches of mathematics and science and different. This was also emphasized in other fields, which I'll come to later. So let me put forward to you a series of very simple, seemingly simple problems from theoretical computer science and how these have been solved in the recent past. In the recent past. So let me start with something called a graph isomorphism problem. All of us know what is a graph. A graph is a collection of points and lines that join them. May I request somebody to mute? Yeah, I think somebody had. Am I on mute or am I okay?
We can hear you. Yeah, we can hear you.
Yeah, okay. So a graph is a collection on the plane of points and lines that join them. And a morphism, as we all know, a morph is to change. And isomorphism means it's the same thing. So this is an example of something called the graph isomorphism project over here. And here are 2 graphs. One is called a graph G, another is called a graph H. And as I said, it's a collection of nodes and a collection of lines that join them. Is the graph G the same as the graph H? In other words, are these 2 isomorphic or not? So this is a question that you can ask, which is very important in terms of computation. This is a very simple case with a small number of nodes and a small number of links. And you can even graphically, you can see that they are the same. Here is a rule that takes you from the graph G to the graph H. And you can show that these are isomorphic. Now, what happens if you have thousands of nodes and thousands of lines joining them? That is a problem for computer science, right? It could be a traffic grid, or it could be planes taking from different airports and landing at other airports, or it could be trains leaving several stations and so on. So you can have several graphs like this, and you want to know whether they are isomorphic or not. So the question is whether you can do this in a limited amount of time or not. Now, thanks to the coronavirus, we all know what is an exponential, right? I bet everybody in the audience knows what is exponential. The very rapid rise, that as it rises even more, and then it rises even more, because the exponential function has the property that all its derivatives keep on increasing, and then you have an exponential rise, basically an exploding solution, which was what the coronavirus looked like in its early months. Now we hope that it's going to flatten out, of course. So the question that is asked by computer scientists is the amount of time that it takes for a graph or any problem, amount of time that is needed. Is it exponential in the size of the problem, or is it a slower growth than that, what they call polynomial time? So this problem was solved recently by this very influential computer scientist, Laszlo Babai, where he actually, this is a famous problem, but it took him some time to actually figure out how to do all these things. And he found an algorithm that would do it in what he called quasi-polynomial time. But he himself found a problem with his proof, and then he was able to correct it himself. This is considered a very important solution. Now, theoretical computer scientists, they talk about various things, but eventually it has an impact, because these things will get implemented on the computer, and it will mean real memory, it'll mean real time, and it'll of course means real money. That's the reason why computer science is such an important subject in terms of the amount of space, the resources that are needed to solve specific problems. Here is another problem, which is called the sensitivity conjecture, which involves something called Boolean circuits. I don't know much about this, but there's a romantic story behind this also for these Boolean circuits. And here's a young man, slight person, so slim and young, Hao Huang, who was able to again attack this problem. And then he describes how he solved this problem of this sensitivity, which is again some outstanding problem in computer science, and how he was able to take the problem of sensitivity and map it into objects that you may play with, such as the Rubik's Cube and other toys with which you play, how he was able to map that problem onto some physical objects like that, and then turn it into a problem that in mathematics are called matrices. And then he talked about how he found the solution, that he was just sitting and thinking about it, and then he just got the solution. So what I'm trying to emphasize over here is those of us who are in this trade, we all are always searching for important and beautiful problems to be able to isolate them, and also eventually to be able to solve them. And then we all are always waiting for this eureka moment when we have finally get that flash of insight. So that is how this person talked about it. There's another problem named after the author of this, which is called the wrinkle graph with 11 vertices. It's called the wrinkle problem with 11 vertices. So this has to do with how many possible ways are there of joining these various points, and how many basic units of connectivity you need in order to be able to completely cover this grid over here. So that is the wrinkle problem. Whether, again, this is a simple example where we can kind of draw this and see that there's a pattern over here and how we could do this. But supposing you had a wrinkle graph with thousands of vertices, how long will it take you for you to be able to do all these connections over there? So this is another problem. So there were these three authors who did not provide a constructive proof that they did not find an actual algorithm to do it, but they proved, again, this is very important in mathematics and theoretical computer science, to prove that something exists. So what they were able to do in all generality, you see, what I have shown over here is something that's very specific. It's an example. But the problems often in mathematics and computer science is to pose a problem in sufficient generality and to be able to make statements about that, so that every example will be, of course, a specific realization. This is where the human mind comes in. And once a theorem is proved about something in all generality, then of course, everything has to become a special case. That's the point that I'm trying to make over here. So these are people who are able to break up this wrinkle conjecture into pieces and completely study this. These are all described very well in the Quanta magazine. I don't know how many of you are aware, but I'd like to inform the participants here that the Quanta magazine is an excellent source of information on all these problems. Sometimes it can be a little daunting to read it, but still that effort has to be made, and so that you can kind of understand what is done in those. So I'd like to urge you all to go to the Quanta magazine website and to be able to read some of these things. Here is something that's familiar. This is named after Srinivasa Ramanujan, one of the greatest mathematicians of all time. And to some extent, I would say, a freak of nature, that a person who was dead at the age of 31 could have done so much work and could have had such amazing influence on mathematics 100 years after his demise. As you know, this year is the centenary year of his demise, and he was gone already at the age of 31. His ideas were so far ahead of his time that there are objects mathematicians find today that they name after him, because there's always a germ of the idea in some of his work, which is then transplanted over here. So here is something called the Ramanujan graph, which entered a recent solution to a 50-year-old problem known as the Cadison-Singer problem, which arose in quantum mechanics and later was transported into theoretical computer science. And these are the three people, Nikhil Srivastava and two other people, who solved this Cadison-Singer problem by using this theory of Ramanujan graphs. So you can read about this also in Quanta. Here is a Ramanujan approximant. Now, all of us know that pi can be approximated by 22/7. It's a reasonably good approximation. Pi, of course, is an irrational number, so you can never have pi to be expressed as a quotient of two whole numbers, but you would like to get as close to it as possible. So this is the notion of an approximant. And Ramanujan had a lot of interest in this particular problem of trying to get closer and closer to pi. Some of the most efficient algorithms for the evaluation of pi to a large number of places in the decimal expansion are associated with the work of Ramanujan. So here is something called the Duffin-Schaeffer conjecture. And these two young people, Kokopoulos and Maynard, they used some of the ideas of Ramanujan in order to solve an important problem of rational approximants, which is named after Duffin and Schaeffer. So we are also in a changing world, rapidly changing world, and a connected world, and an interconnected world. And how are we all connected? The primary way in which we are all connected, of course, is through the internet, which is an enormous beast that connects billions of people. But then it can also connect mathematicians. As you know, the World Wide Web was actually invented at CERN because of these large experiments and large numbers of scientists spread across the world. They would need to kind of share their information on a very urgent basis. So I send you an email, then I wait for you, then you correct it, send it back, and you have 200 other collaborators who are waiting to know what's happening. So the World Wide Web was invented by Sir Timothy Berners-Lee in order to address this problem of this sharing of information by large numbers of people distributed all over the world. But now that it's established, we can use it to do other things also. For instance, here's an example of a problem which is associated with something called the twin prime conjecture. It's an old conjecture which tells you, everybody knows what is a prime number. A prime number is one that cannot be expressed as a product of any two numbers. The only divisors are itself and unity, nothing else. They're all odd except for 2. But there's a conjecture which says that there's an infinite number of primes that differ by 2. 3 and 5, for example, 11 and 13. I don't know, there must be so many more. Just trying to think, but I can't think immediately. 41 and 43 are also primes. And then the conjecture is that there's an infinite number of them, but nobody has been able to prove it. So out of the blue, this mathematician, the number theorist, respectable number theorist, proved something related to this, to the twin prime conjecture. He proved there's an infinite number of primes that differ by no more than a certain upper bound. That's what he proved. And in his case, he evaluated the upper bound using techniques that he knew as 70 million. It's a certain number that came up in his calculation. Of course, it's a large number, but again, it proved in all generality something about an infinite number of primes. So that's why it was so important. So it is important to bring down this upper bound from 70 million to 2. That's what we want to do. So these people, together, they worked on the internet, bringing in brains from all over the world, and then brought down that 70 million to some number like, I don't know where it stands now, 10 or 12 or 16 or something like this. And this young man, Maynard, who was a postdoc in Montreal, he also proved a result using a completely different approach. Now, what am I trying to emphasize by using all these words? Now, Montreal is a small place compared to many other places. It's in Canada, and he was working alone, and he was a young man. He was a postdoc. So you see how many amazing things young people are capable of doing, provided they have the right conditions and the right problems are given to them. So there's this idea that you can have this massively collaborative projects where people can put their brains together and produce a lot of outstanding results. It's something that participants at this workshop should also think of doing, how they can collaborate with one another, do something amazing. But why do we do all this? What is the nature of doing all these things? Well, obviously, I'm not the first person to have thought about it. Many other people who have thought about why we do science as human beings, what is our relationship with the work we do. So here is Henri Poincaré one more time. He's a person who was actually fairly, he had problems with his eyesight. So he was a slightly strange man, partly because of this, that he couldn't see very well. So he had to also develop other senses in order to be able to use his mind most effectively. His cousin at the time was the Prime Minister of France during the First World War. So they were kind of highly educated family with a lot of members involved in all kinds of important things. And so that would also suggest that they would have the best teachers, the best access to resources and so on. And these things make a difference also. So it helps to have any advantage that you can get. So he is described by E.T. Bell in the Men of Mathematics as the last universalist. So after the era of Poincaré, all subjects began to splinter. The era of specialization and super specialization began, but now, more than 100 years later, I think interdisciplinarity again brings people back together. So that's the way the cycle goes. So anyway, so he described his eureka moment as to how he felt when he was stepping onto an omnibus, a solution of a problem that he was working on, it suddenly flashed on him. So the human mind is like that. It is able to do a lot of things. You keep working on something, it may not work, but some other day, some other time, you say, oh, that's how it works. So that's what Poincaré talked about. There are other examples in chemistry. As you know, Auguste Kekulé was working for a very long time on the structure of benzene. He talked about how he fell asleep in front of a fire, I think. And then suddenly he saw a snake gobbling its own tail, and then it occurred to him that benzene must be an aromatic compound with this resonating bonds that we talk about in college. So in fact, scientists work very hard for this moment, which may or may not come. Max Planck was one of the greatest scientists ever. So he says on his discovery of quantum mechanics, now first he found the formula. He didn't know the theory. He found the formula where there was this Jeans radiation formula on the one hand and the Wien formula on the other. And it was the Planck's law which actually got both the limits right. But then he got the formula first and later he figured out how it works in the year 1900. So he says the outside world is something independent from man, something absolute. And the quest for the laws which apply to this absolute appeared to me as a most sublime scientific pursuit in life. So here he's talking about the reason why he did science and what his experience was. Others have looked into the psychology of creativity. How do you become creative? This idea that you have geniuses who are born does not seem to be correct. There seem to be many other factors, including the level of sophistication of a society, its technological advancement, which contribute to the formation of a scientist. So Jacques Adama and Hermann von Helmholtz is known to you from the coil, Helmholtz from the equation, from the ophthalmoscope, so many things he has done in his life. So they talk about many periods in a person's life as a scientist. There's a long period of preparation, and then there's one of incubation, where your ideas are germinating. And they need a time for those ideas to really grow and bear fruit. And then you have illumination, where you suddenly understand everything. But of course, after that is done, you better be sure that it's right. So that's the process of verification. So again, what I talked about earlier, the example of combining the formula of Wien and Rayleigh and Planck, it should have been Jeans, I suppose. Planck announced a formula which is now known as Planck's radiation formula. So this is Planck over here. Within 2 months, Planck made a revolutionary deduction of his formula, and he made an amazing break. He said that, look, classical physics is no good. Just imagine the gumption and gall of somebody to say that the laws of physics that have come down several thousand years from Aristotle to Plato, through the Dark Ages, through the Renaissance, through Newton, and through Maxwell, are not correct, or they are only an approximation of the real world and a limiting case of some other hitherto unknown theory. You can imagine what kind of a revolutionary situation that must have been. So anyway, so that's how he formulated his theory, and he introduced the famous quantum of energy in order to reconcile the two classical limits. Such an amazing feat, such an amazing contribution. So more on this topic of psychology of creativity and discovery. So this is what Einstein said about his discovery of the equivalence principle. I was sitting in a chair in the patent office at Bern when all of a sudden a thought occurred to me. If a person falls freely, he will not feel his own weight. I was startled. The simple thought made a deep impression on me. It impelled me towards the theory of gravitation. So this was his formulation of the equivalence principle. What does Chandrasekhar say in his Truth and Beauty collection of essays? So he says, in some strange way, any new fact or insight that I may have found does not seem to me as a discovery of mine, but something that had always been there, and I just chanced to pick up. So he views this more as a recognition rather than as a discovery. So many of the characters that I've talked about over here, they're all over here at the Solvay conference. Here's Einstein in the middle. That's Lorentz sitting over here. And I don't know who many of this is. Paul Dirac, I see over here. And then there is Marie Curie, which is the one over here. This must be Auguste Piccard, standing over here, a very tall person. So these are all the figures of the early part of the 20th century. So what is the nature of calling of a scientist? This is also something that we all need to think about. As a teacher, you would have to tell your students what the experience of a scientist is. I mean, ours, let us face it, it's not normal activity. It's not like we are a painter, or what we do is immediately discernible to others. It's not like, you're a person who can take a screwdriver and then you can screw something in and things work. What we do in science is quite different. So my colleague Arnab Rai Chaudhary, he wrote an article very long time ago, already 35 years ago when he was a student. And this is what he has to say. We cannot share our intellectual excitements even with our spouses or closest friends. We are perpetually estranged from our fellow human beings. A good scientist, of course, has personal moments of intellectual triumph, but is forever denied those thrills which a triumphant musician standing in front of the stage feels when the whole audience bursts into applause. In popular stories, scientists are very often depicted as awkward individuals, unsuited to everyday life. People who boil clocks for breakfast and keep on doing calculations on sand, even when their lives are in immediate danger. If all scientists were really like this, then they would probably have been eliminated from society by the process of natural selection. However, I believe that these popular stories tell us one truth: the fact that science is a very strange enterprise, although scientists themselves may not necessarily be strange people. So how do we work in science? I mean, I've talked about all the challenges. Is it possible for a person to work? How do we think about it? How do we distribute our time? How do we direct and budget our energy? So Nikhil Srivastava, the person I mentioned earlier, he gave a nice interview, and this is what he says. And I found it interesting because he's a very young person, must be at least 20 years younger than me. So he is much more clued into the reality than obviously I am. So I wanted to read what he says about this. So he says that he does not believe in being a mega workaholic. Instead, he concentrates on having a short spurts of focused, high quality work. Of course, the society has to allow you to do it. I mean, in India, as you know, we have thousands of distractions all the time. What he says is probably more true about more systematic, well-organized societies. For example, even though he loves mathematics, he does not feel it's imperative for him to be doing math all the time. Rather, he finds more productive in thinking deeply about one problem for weeks or months and then taking time off. And this is a crucial thing that I liked very much. You should fail in different ways, but if you know you have tried everything and you're still failing in the same way, then you may have to give up, that a solution may not be there. I've talked mainly about mathematics and physics over here, maybe a little bit about chemistry. Let me say a few words about other subjects also. How does the mind work? What are the phenomenal discoveries in those fields? For instance, there's a theory of evolution or evolution, the most phenomenal discoveries of the human mind. There's also the Mendel's theory of genetics, that living beings pass on their traits to the next generation. Of course, that part is obvious. But how do they pass it on? That there are actually simple laws which allow you to do it. To me, this is an amazing feat. Not that I know much about it, but the fact that he discovered that there are simple laws is what I find fascinating. Or continental drift. Who in his right mind, when our lifespan is of the order of 50 or 70 years, how can we even think of continental drift, which takes tens of thousands of years, or more, that such a phenomenon can take place? If you think of it, you would say somebody who comes up with such an idea, he must be insane. Or that there could have been ice ages within our own human lifespan, or that of a couple of our, grandparents and so on. We know the weather has been roughly the same. To think that there could be ice ages is again another astonishing feat. Today, we know that ice ages can arise because of the Earth's orbit and the precession of the Earth's orbit, or the tilting of the axis, and change in ocean currents, that they can lead to drastic weather phenomena. Think again of the Pasteur's theory of microbes, that the same mechanism is responsible both for beer as well as for diseases or for yogurt. Just imagine what a unifying principle this is, that when he came up with that, how revolutionary it must have been. Or Shannon's information theory, that you can have a systematic way of thinking about information. Each of these is a phenomenal contribution. This is what Charles Darwin says about his own theory. There is a grandeur in this view of life, with its several powers having been originally breathed into a few forms or into one, and that whilst this planet has gone cycling on according to the fixed law of gravity, from so simple a beginning, endless forms, most beautiful and most wonderful, have been and are being evolved. So here is saying that in the physical world, laws may be very simple, but in the biological world, they can be very complicated. It's also necessary at this point to think about the contributions made by women. Almost all examples we have cited are men, but of course, we know that there's a large number of historical, social, political reasons why women have been underrepresented. But even so, good to draw attention to amazing contributions by women. Ada Lovelace, who was born Byron, a daughter of the poet, was one of the founders of computer science as we know it. One of the founders of modern algebra was Emmy Noether, and we already talked about Marie Curie earlier. And finally, this is the person whose picture I had shown right in the beginning, Cecilia Payne, talked about the stuff the universe is made of. Now, Hilbert, the same Hilbert, in the year 1900, he defined 23 problems that he said would define the direction of mathematics. This was settled by Julia Robinson, who unfortunately passed away at a very early age. She showed how this problem is actually undecidable. Then dark matter, the stuff that keeps the universe together in galaxies, was discovered by Vera Rubin. Pulsar was discovered by Jocelyn Bell. We also all know the important work of Rosalind Franklin, paths to the double helix. The first woman to have won the Fields Medal was very recent, 2014, who unfortunately already passed away. She was just in her early 40s. And today, the director of CERN is a woman, Fabiola Gianotti. So here are the pictures of three of these very important women. Emmy Noether over here. This is Maria Mirzakhani and Fabiola Gianotti. What can we say about India? What is our mark in science? Well, we are a country just like any other. We have a confident presence in international science. But there were stalwarts that we associate our scientific history with. We already made a reference to Ramanujan. We all know about Raman and the discovery of the Raman effect, or Saha and his ionization equation, Bose's discovery of Bose statistics, Bhabha, and was also a great builder. There's Rai Chaudhuri. This is also topical because the work of Penrose required some results based on the Rai Chaudhuri equation. We also know the work of G.N. Ramachandran in the triple helix. There's also others, Birbal Sani and paleobotany, and many, many others, Janaki Ammal in cytogenetics. This Venkatraman has written some very nice books on this. So I'd urge those of you who are registered participants to get hold of these books, printed, published by Universities Press. They're not very expensive. You'll be able to get them. I think since that time, a lot has changed. We are now a profession. It is not just a handful of individuals striving. We have a large number of institutions. We have universities where a lot of work goes on. But generally speaking, it is very difficult to get Indian people to talk about their own work. It's probably because we tend to be a little on the modest side. And we are always talking about people in other places, Nobel Prize and this and that. And we don't say what it is that we do. So I think it's also important sometimes to record our own observations about our own work. One of my colleagues here, he has written about his discovery of the nuclear Overhauser effect in biological molecules. As an example of science in the 21st century, I'll take another 5 minutes at most. Here is Venki Ramakrishnan, who is a 2009 Nobel laureate in chemistry. He has some important things to say that I think all of you should also think about. He says it takes courage to tackle very hard problems in science, but he does not think it should be a contest. It's also important to have a multidisciplinary training, take ideas from many fields, and important of hard work. As Seneca the Younger said, luck is what happens when preparation meets opportunity. But why should we do science at all? So this is an answer that was given by Robert Wilson in the context of the US. So he was asked, doing all this pure science, how does it affect the military? How does it affect our security? So he says only from a long-range point of view of a developing technology. It has to do with, are we good painters, good sculptors, great poets? I mean, all the things that we really venerate and honor in this country and are patriotic about. In that sense, this new knowledge has all to do with honor and country, but it has nothing to do with directly defending our country, except to make it worth defending. So that's what he said about his country, and we can say the same about us. This is another wonderful quote that I found for you that I thought would be useful in a refresher course like this. So Victor Weisskopf was one of the early directors general of CERN. He had also spent time in the US because during the war he had to be away, but he came back to Europe, unlike many others. The value of fundamental research does not lie only in the ideas it produces. If science is highly regarded and the importance of being concerned with the most up-to-date problems of fundamental research is recognized, then a spiritual climate is created which influences all other activities. An atmosphere of creativity is established which penetrates to every cultural frontier. Applied sciences and technology are forced to adjust themselves to the highest intellectual standards which are determined in pure research. That is what attracts productive people and brings productive scientists to those countries where science is at its highest level. So let me finish with a few words for young people and those of you who are in the audience who yourself deal with young people, is that they should follow their hearts, and nothing is more fun than research and discovery. That this is the only way to throw open the doors to a new tomorrow. It requires a lot of patience, like running a marathon. And as Thomas Alva Edison said, genius is 99% perspiration. I also want to draw your attention to a speech of Richard Hamming, which is available on the internet, You and Your Research. You can read it. Once again, I quote from Chandrasekhar. The pursuit of science has often been compared to the scaling of mountains, high and not so high. But who amongst us can hope, even in imagination, to scale the Everest and reach its summit when the sky is blue and the air is still, and in the stillness of the air survey the entire Himalayan range in the dazzling white of the snow stretching to infinity? None of us can hope for a comparable vision of nature and of the universe around us. There is nothing mean or lowly in standing in the valley below and awaiting the sun to rise over the Kanchenjunga. Now, this I want to say to people who are constantly saying in India we don't win Nobel Prizes. It doesn't matter, you know. We still have to do it. We can still do the best that we can. So let me end here by quoting once again from David Hilbert. I start with David Hilbert, and I want to end with David Hilbert. And this is what he says, and this appears on his gravestone. It says here, "Wir müssen wissen, wir werden wissen," which is, we must know, we will know. So let me stop here then.
Thank you, Professor Ananthnarayan. It was a lovely talk. You very beautifully wove the fabric of progress in science, physics, maths, chemistry, everything all in one. And you touched upon all the important questions which have involved researchers the best minds to work on them. The Hilbert's problem, and thank you for sparing time and being with us. And we open your talk for questions. If there are any comments, questions, I request the participants to please speak out. You can unmute yourself and speak, or you can write it in the chat window. Yeah.
Maybe there are no questions. Since this is recorded, I guess.
Good presentation, sir, says Umesh Singh Bias.
Thank you.
Mudassir says, thank you very much, sir, for this wonderful talk. So will it be possible to share your PPT with us?
Yes, of course. I can send it to Dr. Najam Hassan and he can pass it on to you.
There's one which asks, when was your eureka moment?
Well, I've had a couple. Once when I was a postdoc in Ahmedabad, there's one calculation that I was doing with Dr. Saurabh Bindani, who was a senior physicist. And there's something that we talked about and I had been trying and thinking. But I remember distinctly I was waiting for a bus at a place called Pandrapol, not far from PRL Ahmedabad. And it suddenly occurred to me how I could do that calculation. And similarly, many years ago, when our daughter was little, we used to take her for a dance class. And while we would be waiting for her to come out, I would be walking up and down in a park nearby. There was some calculation that I desperately needed to do. And it just occurred to me how to go and do it at that time. So I've had a few instances like this, which has been amazing.
There are some more comments. Wonderful session. Thank you, sir, from Mehrun Nisha Begum Rajkumar Pavle says, very informative session, sir. Thank you. Also, Mr. Rajesh De says, very informative session. Thank you. So basically, there is a lot of praise.
Thank you. Thank you. Probably not deserved, but I had sent the same slides to Dr. Priya Hassan in July. It's the same slides that I had sent her earlier. Okay. So yeah. I think it's already available with you.
So if it's okay with us, we'll share it with them.
Absolutely. Absolutely. Yes.
Because it covers the whole thing very beautifully. All the important problems which have people worked on and how they were cracked and the joy, the pleasures you get out of solving these beautiful things. And you ended it so well with Chandrasekhar's comment and also Hilbert's. It's very interesting to read Poincaré or Chandrasekhar. They were excellent scientists, but when they wrote on science, it was like poetry.
Yes. Yes.
I think it's because they could see the beauty in the whole thing. Yes. So yeah, it's so beautiful to read their essays.
Yes.
Okay.
Absolutely.
Thanks a lot for a lovely session.
Thank you so much for having me. It's a great honor.
Thank you. So we'll end for today. We'll meet tomorrow at 10.